Right, so welcome everyone. This is a great pleasure to have you here and back to discuss some things on the board. Now, in a previous video on Not So Fast, we actually looked at the first law of mechanics from Newton. And in particular, that what this law is about is essentially to introduce the notion of inertial frames, which are completely attached to Newtonian mechanics, and more often than not, people simply assume that these things kind of are not important or don't exist, while essentially you can't practice Newtonian mechanics without considering and taking very seriously the notion of inertial frames. Now, the reason why people are uncomfortable, and this is students and teachers as well, are uncomfortable with inertial frames, is because there is no recipe actually to find an inertial frame or to say, oh, this is an inertial frame, this is an inertial frame, and so on. And so we are left a bit kind of hanging in the air when it comes to what constitutes a legitimate inertial frame. Um, that being said, what I'm going to do today is actually start by assuming or admitting that the heliocentric frame, which I call R here, that is centered at the Sun and then pointing in X, Y, and also Z direction towards faraway stars, I will consider that this is an inertial frame. Okay, and for this, if you want support for that particular hypothesis, then this is something done in Newton's Principia in the book 3. So, this was published more than 300 years ago. And in this particular book 3, it's a proposition or theorem of the book that essentially is a center, well, not a center, but at it's stated as the center of the universe in the book, but the bottom line is that that's a place from where you actually should use Newtonian mechanics in principle. And actually, when it does that at the very same time, so this is something put together, it derives or proposes his universal law of gravitation, which we are going to use as well. Okay, but what I'm interested in is that if we start from this idea that the Sun is essentially the heliocentric frame is inertial, so I can use and apply Newton's laws in there, then why is it that in traditional mechanics problems, we actually assume there's a geocentric frame, so a frame centered at the center of the Earth and then pointing in directions parallel respectively to the directions of the heliocentric system. So why is it that we can actually do that? Because the only reason why we can be doing this is only if somehow R prime, so the geocentric frame, turns out to be approximately inertial. And so that's what we are going to do and to look at. And the way we are going to look at it is basically by considering the Sun-Earth system in blue here, and then around it we are going to consider a satellite. In principle, it could be any satellite, but just to get some numbers out, I'm going to look at the moon here. Of course, if it works for the moon, then in principle it should work on any object starting to orbit, let's say about the Earth, or having some stable attachment or that is bound somehow to the Earth. Okay, and that includes ourselves, or at least that works to some approximation, which we are going to see. Okay, so that being said, sorry, here, before I start writing anything, I just put some numbers that we are going to need in order to, let's say, get these approximations going. So here, SE is the distance from the Sun to the Earth. Usually I like to remember that is roughly 8 light minutes, so that's the distance traveled by light in vacuum in 8 minutes. And I like to know as well that or remember at least, that the Earth-Moon distance turns out to be actually 1 light second. So that's the distance traveled by light in 1 second. And then here there are some also masses that I will need as well. Okay, so what we start doing is, because R is inertial, so I'm going to start writing things from R. So I'm going to say in R, that is inertial. Okay, I can apply Newton's second law. Okay, so we can apply Newton's second law. And which says, in our case, and I'm going to apply it directly to both the Earth and the Moon. So here I'm going to write R. So I write the vector R here. I hope you can read. So R here is the let's say R SE. So first for the Earth, okay. And here this is dot dot. So that's the second derivative. And then here that's the mass of the Earth, and that's equal to, and here I need to add up the forces acting on the Earth. And there are two forces. There is the gravitational force from the Sun and the gravitational force from the Moon. So that's going to be minus G, and then I've got MEMS, and then here that's going to be divided by R, and I'm going to call that SE as well. So by the way, RSE is what I call SE here. That's cubed. The reason why I cube it here is because I'm going to put the vector RSE here. And then I do the same for the Moon. So I've got minus G, then MEMM. So that's the influence of the Moon onto the Earth. So that's RME cubed, and that's RME. Okay, so that's one equation. Then the second equation is then the equation of motion for the Moon. So that's so that's MM, R, so that's SM dot dot, because we are expressing things in this inertial frame, and that's going to be equal to minus G, so that's MM ms divided by RSM. So let's put things, yeah, so that's SM cubed and RSM, and then minus G, and then that's ME. But that's the influence of the Earth on the Moon this time, and so that's REM cubed, and then REM. Okay? So we are almost there. So what you notice, and that's something very common, is that here you've got MM, and that's also appearing here and there. And likewise here you've got ME, ME, ME. So I can basically get rid of them, which I'm going to do in this fashion. And then here, okay? And once we have done that, then what we can try to look for is the relative acceleration of the Moon with respect to the Earth, okay? Because in that case, we are changing the frame of reference from the heliocentric frame to the geocentric frame. So the way to do that is to say that the relative acceleration of the Moon relative to the Earth is going to be, we simply need to use normal Euclidean and Galilean kind of transformations here. And we are going to get that this is R dot dot then SM minus R dot dot and then EM. No, sorry. Bad. That's SM minus SE. Okay, so we've got here these accelerations, and so I just need to add up all of that stuff. So what I'm going to get is basically I'm going to get, so I start with SM, so that's here. So I've got minus G ms divided by R SM cubed, and then R SM. Then I've got this term as well, so minus G, then ME divided by R EM cubed, and then R EM. And then I've got plus G ms RSE cubed, and then RSE. And then finally plus G MM RME cubed, and then RME. Okay, so that's basically all the terms that we have. And what we want to determine is kind of whether or not any of these terms are small compared to the others, and also whether some terms kind of happen to compensate each other. So, for example, what we know is that we have the I'm going to present it in the following manner. So we've got that RSM. So let's put it here. We've got RSM is RSE plus REM. Okay. So what that means is that I can basically employ that here. So I'm going to get minus G, then MS, then RSM cubed. And then here I've got basically RSE. In fact, I'm going to, how to put it? I'm going to say here that I've got REM. Okay, I'm going to keep this one here, so minus G. Yeah, so let me put everything together. So by substituting this, I'm going to be able to factorize things out. Okay, so I'm going to get it's equal to minus G, and then factorizes. I've got ms rsm cubed. Okay, so that's what I have. Then I've got minus. So let's see. So yeah, minus. So that's a plus here. Plus me over rem cubed, and all of that is actually multiplied by rem. Okay, so I've simply put here the EM part is going to come here, and I can factorize with this term. So I've got a compound term here with an influence from the Earth and some component coming from the Sun. And then once we have done that, we can group these things together because there is the RSE coming from this RSM. And so I'm going to get here, let's say minus G, and then I'm going to have ms over rsm cubed, and then in that case this is RSEs, and then I've got minus this term ms over RSE cubed, and then all of that factored as e. And finally, there is this term here that is left kind of out. Cube RME. Okay, so these are all the terms that we need to look at. So the first thing that I can say is that what we can try to do is try to compare the kind of the different terms. So here I'm going to denote this one A. Okay, so that's a term I'm going to call A. This term I'm going to call it B. Then I'm going to look at yes, this one as well. So here I've got C, and then here I can also say that I've got D. Okay, and then here I've got E. And by the way, here this is a capital M. And essentially what I want to evaluate are what are the ratios and the orders of magnitude of all of these different terms. And in fact, what I tend to be interested in is to compare all of these terms with respect to B, or B times the magnitude of this. Okay, that's kind of what I'm going to care about. And so one of the things that is going to happen is that indeed the sun has an incredibly strong kind of effect on things. But as it turns out, you see here that there is going to be a kind of a compensation between the two. And essentially that's what is going to to do things relatively to make things relatively easy, essentially. So in the end, let's compare, for example, A with B. So here, so here we are going to evaluate orders of magnitude. And we are going to start by the magnitude of A divided by the magnitude of B, and try to estimate what it is. So if you look, what we are going to have is we are going to get so A, we are going to get ms here, divided by RSM cubed, and then here we are going to get REM cubed, and then divided by ME, right? So here I'm only caring about orders of magnitude, so I just need to substitute. So I've got 2 times 10 to the power 30. All of these are ratios, so I don't care too much about these things. So I've got 2 to the times 10 to the 30. Then I've got REM cubed. So that's I've got REM cubed, so that's 1 cubed. Okay, so nothing crazy about here. If I use, in fact, what I need to do is that when I say 8 light minutes, I need to convert into seconds. So that's going to be useful for us. So then I've got ME. So ME is 6 times 10 to the 24. And then times, so here I've got 4 times 240, so that's 480. Okay, so that's basically that's 480. So that's the number of seconds in 8 minutes, and then cube. Okay, so in 8 minutes, yeah, that's 480, and then cubed. So we need somehow to evaluate this. And what this is equal to, so 3 well, let's say this is basically 10 to the minus 3 in terms of order of magnitude. Okay, so the next that I looked at was, again, this is just to that it goes faster because this is just plug-in numbers. So we've got d over b divided by, so that's e, and then I've got m over b, so that's me, okay, and then we've got rem cubed, and then rme, which is the same actually here. So that's only equal to the ratio, the mass of the moon and the mass of the Earth. And you see you've got a ratio here, which is about 10 to the minus 2. Okay, then what you can look at is basically so you can try to do it yourself, but you can try to estimate the ratio of C no, probably I will have to do it kind of directly. So we need actually to evaluate what is the typical value of C minus D. Okay, so that's something we need to evaluate. And again, the absolute value of this. So we need to estimate what this is, this thing. I think there is no escape from that. And this particular object is going to be, I could have factorized by ms, by the way. So what we have is that we have ms, so g, ms. Well, it doesn't matter g, to be honest, because g is not in these factors. So here we've got, so forget about the ms for now, because what we care is the difference between this 1 over r sm cubed and 1 over r se cubed. Check time. So we are going to get sm, and what I'm going to say here, that's a simplification, or at least a way to get the order of magnitude. I'm going to say that sm can be viewed as being se, so I'm going to say that rsm is going to be rse, and then in the best and worst case scenario, if you will, in terms of interaction, I would add or subtract the distance from the Earth to the Moon. So I say plus or minus the distance from the Earth to the Moon, and so that's to the power minus 3, okay? And I need to subtract that from 1 over RSE cubed. So in fact, I don't need to do anything special here. I just have RSE cubed. Okay, and so that's not even approximated yet. So again, the ms part is going to be constant here anyway, so it's not going to contribute. And so what I'm going to get here is that RSE I can factorize, so I'm going to get RSE to the power minus 3, sorry, that I factorize. So here I've got 1 plus minus REM over RSE, and then to the power minus 3, and then minus RSE to the power minus 3. Okay, so let me continue. We are almost done, to be honest. So here, all of this is exact so far. And then what I'm going to do is I'm going to say that 1 plus minus REM over RSE to the power minus 3 is approximately equal to 1 minus plus 3 times REM divided by RSE, and that's it. And that's if the ratio between REM and RSE is much smaller than 1. Okay? And here we do actually meet this criterion because we've got a factor 480 between basically RSE and REM. Okay, so 480 seems to be big enough to be to do such an expansion. And so what I get in the end is that I've got that this C minus D is going to be something like this RSE is going to be multiplied by 1, but then subtracted by the same guy. So nothing really is going to happen here. So these are going to cancel out. And then I'm going to have, in terms of magnitude at least, I'm going to have 3 times. And then I'm going to have REM. And then I've got RSE to the power 4. Okay, now you can check the dimensions. I'm still fine. Okay, so I started with basically things that were in 1 over a length cubed, and I still end up with something which is 1 over a length cubed. So the final bit that we need to look at, and then we are done, is basically compare this particular quantity, so the difference between the two, and I want to take the ratio with B. So I want to take this particular ratio and compare it with B, okay? And then and see how that goes. So what we are going to get, I need to take the M into account, and I need to take into account the magnitude of RSE as well. So here I do, if I want to be a bit clear, I do this times RSE, and I want to compare that to B times REM. Okay, because that's kind of the magnitude of the total expression here. And so then if I look at this, I actually get the factor 3 is completely unimportant. But essentially, I'm going to get REM times RSE. So that's the product of these two in terms of order of magnitude. And then I've got RSE to the power 4. Then I've got REM. And then I've got B, okay? And so B is going to be, I need to have, I've got MS. Then I've got ME. And then I've got finally REM cubed. Okay? So what we have is that in the end, we've got some REM to the power 4 that is cancelled here. So that's REM cubed, in fact, cancelling here, divided by RSE cubed. Okay, and then we've got the ratio of MS and ME, but actually that's what we had exactly here. So it turns out that the order of magnitude of C minus D over B with the corresponding RSE and REM here, so to compare really this with that, we actually get that this is 10 to the minus 3 as well. Okay, so the bottom line is that, of course, we could, so the bottom line is that we've got that this term are all, where am I? So essentially there is a ratio which is at the very least 1 in 100 between the magnitude of any of the terms there and the magnitude of that term, okay? Which is simply the gravitational acceleration due simply to the Earth pulling the moon, and that's it, okay? And essentially we're done, right? So at the end of the day, what I get is that, and that's the final conclusion, we've got that if I've got an object in orbit like the moon, I'm going to have its acceleration with respect to the Earth. So that's in the frame r prime is going to be minus, in very good approximation, just GME over REM. Okay, and so that's cubed, and here REM. Okay, and that completes, if you will, the derivation and the demonstration. because here we see that the acceleration is uniquely characterized by the universal force of gravitation. That's it, nothing else. So that's what you want when you introduce, when you've got an inertial frame, you want that it depends only on the universal forces you're aware of. And finally, it also, in that particular case, and that's again a signature of being in an inertial frame, it does not depend on the motion of the Earth relative to something else, okay? Which usually you would have in an inertial frame, in a non-inertial frame, okay? So the bottom line is that that's why we can actually do that, is because there are plenty of terms that kind of are either small, and that's because, for example, the distance is very large to the moon or something, or there is compensation. And this C minus D, which is best, this C minus D term here actually is very important because it's compensating what it's saying that you've got here the Earth orbiting the Sun, okay, but this Earth in a sense is exerting the same acceleration on the M here, okay, and so essentially there is already a compensation by the orbit of the Earth that is somehow compensating the fact that the moon is also subject to the same attraction from the sun. And so the bottom line is that both of them are falling together, and so it's as if they were inertial. And by the way, this is exactly the kind of things that appear in Einsteinian mechanics, where the definition of an inertial observer is a little bit more transparent, and where it says that an inertial observer is an observer in free fall. Okay, and so here, if you assume that both of them are in free fall around the sun, and that they are close enough to each other, with one of them being bound to E, then you end up with the same kind of idea that basically the geocentric frame is a good uh, approximation for an inertial frame. Okay, so that was a bit longer than before, but that's what happens when we do things on the board. But hopefully you understood kind of what's going on. There are plenty of terms coming in principle, in the true exact acceleration, if we start from the heliocentric frame, and then many of these terms turn out to be negligible when compared with the term that is only due to the gravitational force from the Earth on the moon. Okay, and essentially the main compensation appears here because you've got uh, the motion, if you will, the rotation motion induced by the sun on the Earth that is compensated by the uh, similar rotation motion that is induced by the sun on the moon. Okay, so these two terms cancel out, mostly cancel out, and basically give something very negligible as well. Okay, so that's it. If you've got any questions, please let me know. But that's it for today.